Tsunamis are nature's most ferocious force, driven by the intense physics of our planet. I'm here to uncover the jaw-dropping science behind these monster waves, how they form, why they grow so massive, and how we're fighting back. Buckle up for a wild ride, hit that subscribe button, and let's dive into the awe-inspiring world of tsunamis. In 2004, a tsunami rose over 30 meters, tragically impacting over 340,000 people in hours. It wasn't just water, it was physics unleashed. From underwater earthquakes to towering waves, tsunamis are a dramatic dance of energy and motion. Today, we'll unravel the science behind their creation, explore their overwhelming power, and reveal how we're trying to outsmart them. You won't look at the ocean the same way again. Tsunamis start deep beneath the Earth's surface, where the planet's crust is broken into massive pieces called tectonic plates. Picture 7 major plates, like giant puzzle pieces floating on a molten core of lava, constantly shifting due to convective heat transfer. These plates move just inches per year, but their interactions are explosive. There are 3 key movements: diverging, where plates pull apart, like the East African Rift Valley; converging, forming mountains or volcanoes, like the Cascade Range in the USA; and subduction, where one plate slides under another, creating the perfect conditions for tsunamis. Subduction zones are where tsunamis are born. Imagine an oceanic plate, denser than the continental crust, sinking beneath it. This movement creates deep ocean trenches, like those in the Pacific Ocean, and bulges the continental crust upward, storing massive strain energy, sometimes for centuries. Think of it like tightening 2 stuck wooden blocks until snap they release, unleashing energy in seconds. When this happens underwater, like in the Japan Trench or Chile Peru Trench, the seafloor lurches upward, displacing huge amounts of water and launching a tsunami wave. In the open ocean, tsunami waves are sneaky, traveling at speeds up to 800 kilometers per hour, faster than a jet, but with an amplitude of less than half a meter, barely noticeable. Why? Their wavelength stretches hundreds of kilometers, spreading their energy, but as they approach the shore, the water depth drops, and physics takes over. In our wave tank experiment, a wave in deep water reaches the end in 1.9 seconds. In shallow water, it slows down. The wave's frequency stays constant, so to conserve energy, its wavelength shrinks and its amplitude skyrockets. This is wave shoaling, the intense physics that turns a small wave into a towering giant, surging onto land with tremendous force. Here's a mind-bender. Tsunami waves don't actually move water forward. If you drop balls in the ocean, they just bob up and down as the wave passes. The wave transfers energy, not matter, across the ocean. But when that energy hits shallow water, the massive amplitude, sometimes over 30 meters, unleashes chaos. It's physics at its most powerful, turning a ripple into a force of nature. Let's revisit the 2004 Indian Ocean tsunami, the most catastrophic in history. A 9.1 to 9.3 magnitude earthquake off Sumatra, Indonesia, lasted 10 minutes, one of the longest ever recorded. The Indian plate dove under the Burma plate, thrusting the seafloor upward and displacing water with the energy of 23,000 Hiroshima bombs. Waves up to 30 meters high hit Indonesia within minutes, Thailand in hours, and even reached Africa. Over 340,000 lives were tragically affected. This event showed the raw power of subduction zone earthquakes and the urgent need for better warnings. Earthquakes cause 80% of tsunamis, but they're not the only culprits. Underwater volcanic eruptions can collapse or erupt, pushing water into massive waves. Landslides, like the 1963 Vajont Dam disaster in Italy, where a massive rockfall created a 250-meter wave, are another trigger. Even rare events, like a meteorite splashing into the ocean, can spark tsunamis. Each taps into the same intense physics. Sudden water displacement equals catastrophic waves. You've heard the saying, if the shoreline recedes dramatically, a tsunami's coming. It's true, sometimes the wave's trough hits first, pulling water back before the crest surges in. But not always. Sometimes the crest arrives first, like in 2004. After that disaster, nations deployed dart buoys, deep ocean assessment and reporting of tsunamis. These buoys use ocean floor pressure sensors to detect water level changes, relaying data via satellite to warn coastal areas. In 2004, waves took 20 minutes to hit Sumatra and hours to reach India. Early warnings can save lives by giving time to evacuate. Can we stop tsunamis? Japan's trying. After the 2011 Tohoku tsunami, which affected over 15,000 lives and topped 15-meter seawalls, Japan rebuilt a 400-kilometer-long wall, up to 15 meters high. But 2011 showed even advanced systems can fail. Early warnings underestimated the wave height at 3 meters. If Japan's tech can miss the mark, what about less advanced regions? Sea walls and early warnings reduce impact, but physics says we can't stop nature's power entirely. Tsunamis are physics at its most dramatic, but understanding them can save lives. From tectonic plates to wave shoaling, we've uncovered the science behind these giants. Want more mind-blowing science? Smash that like button, share this with your friends, and subscribe to our channel for more epic deep dives. Grab our free tsunami science guide in the description. Comment below, what shocked you most about tsunamis? Let's keep exploring together. See you in the next video.